Hello, and it's time to learn about volcanoes and volcanic hazards. So in one of my many prior lives, this is what I wanted to do for a living, was to become a volcanologist. And I have done some work and study and research in this field and just find it to be one of the most appealing parts of geology, personally to me. Volcanoes are very different depending on what kind of body plan they have, so we'll be talking about that shortly. But I wanted to start off with a place that's really beautiful, Mount Hood, and wanted you to see it and look at that body plan for a little bit and think about how this thing might erupt. Not all volcanoes are equal, meaning they don't erupt the same way, and even a volcano itself could transition over time in terms of its explosivity. Linking back to what you learned about igneous rocks, specifically the chemistry of Felsic, intermediate, mafic, and ultramafic categories, all based on the amount of silica it has. That dictates how a volcano behaves. So one of the first things we have to do when we're talking about volcanoes is understand some general terms that are applied to determining if something is an active, dormant, or extinct volcano. So let's start with the active, because those are the easiest ones to define. Active volcanoes are those that have been active in historic time or currently have evidence of being active. Let me give you some examples and clarify that. Active cannot just mean a lava eruption. It could be gas. It could be other types of activity that's exhibiting thermal, maybe hot springs and geysers and fumaroles if they're near mud pots, if they're near that area. And I'll show you one of those here shortly. Dormant means that the volcano has not erupted in written historic time, but certainly has the potential to do so. Not all volcanoes are dormant that haven't been erupting. If you hear about an extinct volcano, that means there's no hot spot that could generate it. It hasn't erupted during historic time. There's really no way it will because it's not near a hot spot. So let's get to that business first. Hotspots are those mantle plumes that have been rising up from the mantle, heating up the lithosphere, whether that be continental or oceanic crust. And as that occurs, volcanoes can form. So not every volcano will erupt, but most erupt and erupt multiple times. So let's take a look at some of the issues regarding volcanic eruptions. The first thing would be the gases that they erupt. So I'm at the Hawaii National Park, and this is the main crater. So this is on Kilauea. And present day volcanoes like this one, you can see that it's very active. Now you're not seeing lava in this picture, but this particular system, this crater, it fills up with lava quite frequently, making it a lava lake. And what will happen is you see this is smoking. Well, that's evidence of activity. Unfortunately, that smoke produces chemicals, things like carbon dioxide, carbon monoxide, even things that are not healthy like chlorine and nitrogen oxide. It can produce all kinds of greenhouse gases and things that are unhealthy to breathe. But one of the main things that come out of volcanoes are water vapor. And water vapor is a key ingredient in greenhouse gases, one that's not often talked about, but has the potential to hold a lot of heat. So I went to that crater and went to this place multiple times. And I have been there and hiked. There's a trail that you can hike to get to here. And with a group of people, we were hiking it from the headquarters. It is a long way from the headquarters. And we took all the necessary supplies. We were prepared. But we got about 2.5 miles in. All of us started coughing. Our eyes started burning. some of us had to sit down and kind of regroup, and within 5 to 10 minutes, all of us were literally not feeling well. And we had encountered something called volcanic smog, which is VOG, V-O-G. What happened was we were breathing in a high concentration of sulfur dioxide, and it had chemically released with sunlight and oxygen to form an aerosol that really irritated the lining of our lungs. About that time, a park ranger with their mask on, meaning their gas mask, was on the trail looking for people like us and asked us to evacuate immediately. Well, that day and night, and subsequently days following, this thing had an eruption. Kilauea was very active, and I got to actually see an active volcano, lava fountains, lava tubes. It was really fantastic. So at night, this thing glowed because you could see the lava at the bottom of the lava lake. But the signage the next time I went was very clear because there was so much activity that they had to warn people that there are times when the volcanic fumes can be hazardous to your health. So another risk that we have with volcanic gases is this: aerosols mixed with particulate matter. PM, or particulate matter, are the fine material that can stay aloft in the air. So it can be like dust and smoke, and in this case, ash also. And so volcanic ash typically has a very light color, meaning it's usually light gray, but most of the time it's super light in color, which is important because when you get a volcano that erupts a whole bunch of ash, typically that helps reflect sunlight in the atmosphere back to space, which means that we have less solar radiation coming in. So that can actually cause a climate cooling, where the volcanic gases themselves that are greenhouse gases can actually lead to some climate warming because they absorb solar radiation. Thinking about that, if you don't have a volcano that erupts a whole bunch of ash, but it erupts a whole bunch of greenhouse gases, you could have climate warming occur where if you have a bunch of particulate matter from ash, like a giant volcanic eruption similar to Mount St. Helens or Mount Pinatubo in 1991, you could produce some very catastrophic changes to the air quality, subsequently short-term changes to climate on a global scale. As evidence of that, I'd like to share some examples of how volcanic pollution wreaked havoc on human civilization. So this is a shot I took in Iceland at a place that was extremely active in 1783, and I might add since then. This is Loki Volcano, and this is really kind of in the middle of Iceland. It took us several hours by bus to get on a very rugged road out here. Then we had to hike miles from there to get to this place. And it erupted for about a year and created just dozens and dozens of fissure openings, which shortly I'll show you some video footage of different types of eruptions, and we'll show you the typical type of Icelandic eruption in terms of being fissure. But the amount of basaltic lava that came out, and take a look at the dark gray, when you get up on it, it's black lava that came out. And it produced clouds and plumes of this poisonous hydrofluoric acid and sulfuric dioxide gases. So when this happened, this created poisonous gases that wasn't just poisonous to humans, but also to livestock and to crops. So essentially, the blue haze that happened in Iceland that year created a famine because it killed off crops that people depended upon. A similar type of thing happened in 1815 in Tambora. And Tambora is in Indonesia. And so volcanic gases created this dry fog that led to an unusually cold winter. Because remember I said that you get this aerosols and particulate matter in the atmosphere. Well, Tambora was a huge eruption. And so this particulate matter lingered in the atmosphere, reflecting more solar radiation back to space, and that was referred to as a year without a summer. So they basically didn't have a growing season. and that led to crop failure and famine throughout that part of the world. So a very important concept regarding volcanoes is viscosity. So viscosity is basically a measure of the internal resistance of flow of a substance. So I'll give you some substances that you can relate to. Peanut butter, highly viscous unless you nuke it in the microwave, and then it becomes a lot less viscous. Same thing with crystallized honey. That would be very viscous, but you get it hot and that thing will flow. Well, lavas do the same thing. And we also need to define the difference between magma and lava. You've seen that earlier this semester, but let's just review it. Lava is the stuff that you're seeing like on the right. It's molten rock that's come to the surface. The magma is what's inside the earth that's molten. So yes, they are all molten rock, but the words matter because when something comes to the surface, that lava can have different characteristics than the magma underneath the ground because it cools so much faster. So we're going to kind of use them interchangeably here, magma / lava. Just wanted to clarify what they mean. So the percentage of silica that the magma or lava has determines a few things about viscosity. So let's start on the right side and then work our way left. Notice how molten this lava is, how red hot. This stuff is going to be well over 1,000 degrees Celsius. So we're probably looking at about 1,200 degrees when it comes out Celsius. And this thing will have less silica because it's not very thick. Matter of fact, it's pretty thin and it's super hot. And the reason that it's thinner, meaning the lava itself is not honey-like or molasses-like or peanut butter-like, is because it doesn't have much silica. This allows for lava to flow and travel. Sometimes it can travel for tens of kilometers away from the source of the eruption. And that's certainly the case in Hawaii. That's how this island and all of the islands like it around the world that are volcanic can grow in size, is that volcanoes can make lava tubes, which we'll learn about. They can get lava flows that are very runny because they're highly mafic, almost ultra mafic, and they can flow and reach the ocean in some cases, growing the edge of the island. So let's look at the left picture here. The left picture spells a completely different story. And you look at this eruption and you see this plume of ash and gas and material. So what happened was the pipe of the volcano got a lot of molasses, crystallized honey, or pasty peanut butter in the form of lava that started to crystallize. So the reason is, why did it crystallize and make a plug like a champagne bottle? It did that because of the high amount of silica in the magma. So the higher the percent of silica, the cooler the temperature. That cooler temperature allows for the crystallization of the minerals, which is a barrier for the gases and the lava. If there's lava there, anything behind that plug is being expanded and building up pressure. So it takes a lot of pressure to blow it from the inside out. And when it does, it creates a highly explosive eruption. So while this is hotter, and sure, you can die if you get into lava, of course. If you were anywhere near this or on the mountain when this occurred, I would say your chances of survival are not very good. So the silica matters. That's the point. Viscosity determines all the factors that we care about when we're talking about how explosive or not explosive. And this is explosive, this is not explosive in terms of a volcano. All right, let's talk about the lava temperature again and viscosity. The less viscous a lava is, the more it'll do, like you see here in Hawaii. This is a famous vent that erupts regularly in Hawaii, producing lava flows that have actually grown the size of the island. The reason it's hotter is it has a lower silica content, so its chemistry is mafic. It's almost borderline ultramafic. And this hot temperature allows the lava to flow and erupt and make lava fountains. Sometimes you get a little bit of pyroclastic material, but not very often. Instead, you get very unique lavas like this one, Pahoe Hoi, and you can get lava, which is very blocky lava, but it's all mafic material that typically comes out of these low silica eruptions. So let's shift gears and look at the opposite. Let's look at lava and viscosity that have temperatures that are much lower, and I might add more viscous and thicker because they have a higher percentage of silica. So these would be your high percentage intermediate volcanoes, meaning the chemistry of the lava or magma or felsic. And instead of seeing that lava fountain, this is what you're going to see growing right here, which is a lava dome. And that lava dome's a clue because the lava dome is going to be something that could create a very violent eruption when it releases. So let's apply what you learned here. Would this have been a low or high silica eruption? I took this shot in Hawaii, that's one clue, but look at the color of the lava, that's another clue. And I can tell you this thing traveled kilometers from the source, which was that same vent I showed you a few minutes ago. And it redecorated one of the roads. So if you're in the park, they had to build another road to kind of go around this, but you can get out and look at it, and it's really pretty cool. So if you said low silica, you were right, because this thing was super hot. It could flow for long distances, and then finally it cooled off, and we're not but just half a kilometer or a kilometer away from the ocean. It just didn't quite make it there, but part of the lava flow did. All right, let's compare the factors of what makes volcanoes unique. So I realized that the colors, there's a blue box with red letters above it, and then there's a red box with blue letters above it. So let me explain why I did that. Let's start with the more explosive. I put that in red because those are the more dangerous or the more hazardous, and put the blue box around it because the temperature is much lower. So let's look at a more explosive eruption. It has a higher percentage of silica, thicker lava, it's more viscous, very much lower lava temperatures, and the gases are expanding inside behind the plug and that volcanic pipe. So once that plug releases, it is all heck breaking loose, and it creates a highly violent pyroclastic type eruption. So in the red box, we have hotter temperatures because we have less viscous lava. So it's not as thick, it's more runny, it's thinner, has a higher temperature, and the dissolved gases don't make it nearly as explosive. So silica kind of dictates all of those factors, how the gases behave in the lava, the thickness, and also the temperature. So let's apply what you've learned. This thing is kilometers away from the source. And would you call this a high or a low silica type eruption? And you're like, well, it's the same as the other one, and you're right. It is. It's a very low silica mafic eruption. And you can see how lava flows could be very damaging to humans and their structures. But one thing about lava flows is typically people can be evacuated before they occur. So while property might be lost, the loss of life is less than what you would see with the high silica eruption, where there's pyroclastic material that can literally bury everything in its place. So if you're thinking back to igneous rocks, we talked about chemistry of igneous rocks, specifically the percentage silica they contain. And felsic was the highest percentage of silica. And it also produces rhyolitic type of rock. If it's the intrusive version or plutonic, granite forms there. But think about this. Because it's so high in silica and low in temperature, 650 degrees to 750 degrees Celsius, that is certainly cool enough to crystallize minerals in the volcanic pipe. And this will act as like a champagne cork. And so to get that out, the pressure has to build up inside of that volcano until it goes. And we have a massive release of pyroclastic material, which is exactly what you're seeing here. Look at the pinks, tans, whites, and very light shades of gray, all characteristic of the ashes and the silica material that comes out of felsic volcanoes. I should also point out that this rhyolitic material, usually you don't see as much of the volcano left after a felsic eruption. Not always, but most of the time the whole thing blows away because it is so explosive it leaves a caldera behind, and usually giant calderas. So intermediate eruptions have temperatures that are in between felsic and mafic. And because of that, their 750 degree to 950 degrees Celsius allows them to have a very unique set of personalities when they erupt. So let's do the 750 first. Intermediate eruptions are going to produce things like andesite. So they're moderately violent depending on how hot or cool their temperatures is. So let's look at the cooler side, which is 750 degrees Celsius. So that's going to have more silica, and it's going to be cooler in temperature as compared to the 950. So the 750 will be more violent and the 950 will be less violent. Don't get me wrong, intermediate eruptions are dangerous because they can produce pyroclastic material. So when they do, they typically come out in those 50 shades of gray, and these are examples of intermediate lavas and material of andesite, and sometimes we get stuff that's almost borderline felsic, that's more like dacite. So when you see this, it's very indicative of subduction type volcanoes along subduction zones of the world. So let's move into mafic or basaltic eruptions. Mafic erupts at a range of around 950 degrees to 1200 degrees, and sometimes slightly hotter. And I'll tell you, this beautiful lava, the Pahoi Hoi, comes out a little hotter than the Ah, which is another type of mafic eruption that makes the blocky lava, but you can see how hot this is. And the temperature of being so hot, near the 1200 degree range, it's going to flow and can flow for kilometers away from its source. So it's not going to be nearly as explosive as a volcano that is 950 degrees in mafic. So if you got a 950 degrees, you could have some pyroclastic material, but you're not going to see nearly as much as you would in intermediate and certainly felsic. Well, we have to talk about ultramafic because there are very few places in the world today that there could be ultramafic, but we do have places that come close or are at that borderline, like Hawaii, even places in Iceland and other locations that have mantle plumes that are connected to a batholith that are deep inside the mantle. So they're pulling up ultramafic material. Ultramafic is very high in magnesium and very low in silica. So it's more runny because it's ultra hot, around 1600 degrees Celsius. This would be the least explosive, but if you were to see one of these in modern time, let's just say it happened, you would see lava fountains and rivers of lava that look like this. So you have to know that most of our lava that's ultramafic happened during the Precambrian eon. And like I said today, they're just borderline. Most of them that are like this are really on the low silica side of mafic, so they don't reach the temperatures of true ultramafic. So let's apply what you learned. You see a bunch of pyroclastic debris. Look at the layers of pyroclastic ash here, and notice the color. So the colors matter, right? So felsic is white, tans, pink, some very light shades of gray. Mafic's the black and super, super dark colors of gray. Intermediate's everything in between. And then your ultramafic are dark blacks with greens. So what do you see here? If you said felsic, you're correct. This was a highly explosive pyroclastic material, so it would have come out of a felsic volcano, lower in temperature and high in viscosity. All right, we're going to learn about some lava features. We'll start with lava fountains. These are formed when a large amount of lava that's super hot, like Mafic, can shoot up into the air, and they have lower silica. If they were higher silica, you wouldn't likely see this type of thing. I'm not saying you would never see one in an intermediate. That's not true. They're just more common with low silica eruptions. Lava lakes are another feature, and lava lakes are formed when large amounts of lava pour into a crater and produce something that looks like this. This is in Hawaii. You find these all over the world, and the lava lakes are filling up with lava. They can drain back into their system underground, their plumbing system, and so these things can rise and fall. Sometimes they rise above the lake and spill out onto the ground. But typically they are super hot, they're molten, they are usually lower silica materials. For lava tubes, they're like caves underground. And they form when you get very low silica lava like basalt doing this. This is a shot I took from a helicopter, and you can see that parts of the lava flow are starting to crust over. These parts have, and there's actually lava flowing underneath them. These are lava tubes in the make right on either side. You can see an orange kind of halo coming up from that. And what's happening is it's forming this same situation over here. Both of these are from Hawaii. And when you look at this, the roof stays intact and the lava continues to flow underneath it. And the roof is made of hardened lava. So this allows lava to stay molten and travel much further than it would if it was just on the surface. It acts like a coffee cup, an insulation feature. So I thought I would take you to Subway Cave, and I'll do a little video shot in a few minutes to show you Lassen Volcanic Park in Northern California, because it has every type of volcano there, so it's pretty cool. And you can go in and see that this is the ancient lava tube right here. And when you get to Subway Cave and you get in there, it's like, wow, it's dark in there. And yeah. So this is the inside of Subway Cave, and you can notice that that is lava. And so this lava would have been traveling through the actual cave that it formed. And eventually this whole thing will collapse because the weight of the ceiling of the lava tube will collapse. People often ask me, how tall is the Subway Cave? It depends on which part you're in, but in the exit, you can get a pretty good gist of that because the height comes to about 2 flights of stairs. And so it's really dark in the cave when you get in there, but it's cool. It's a really neat place in Lassen Volcanic Field. I am at the Lassen Volcanic Field in Northern California, part of the Cascade Range. And a couple of things I'd like to note about this stop. First of all is the monitoring device in front of us right here. This is a GPS unit and a seismograph station. So they got a seismometer that measures earthquake movement because this is still a very active system. And they've got these across the park, but this was the one that was the easiest to see and get close to take a shot of for you guys. My question to you is, why would they be measuring this and why here? I'm at Sulfur Works in Lassen Volcanic Field, and obviously there is a fumarole vent, and the mud pots you see going off down here are pretty fluidy, and of course it stinks like sulfur dioxide, like rotten eggs. One thing I'll make a note of, I'll come back to what you're seeing. I want you to take a look at the ground and notice that it is compromised. We see all those mud cracks. And the reason is because we have almost a sulfuric based acid coming up to the surface where groundwater has mixed with the volcanic fumes. So that's what mud pots look like. That's how they behave. This thing can grow in size, and I would say it would not be the wisest choice to be walking on ground that has texture or surface like this does. People do sillier things. There's signage that says not to, but there's a reason why it's there. I want to focus in on the stream. And I want you to note the color that you see is kind of a rusty orange. That's not the color of the water of the creeks around here. It's very clear, beautiful water. That is not. That's coming from the mixture of materials that are reacting to the material that's in the volcanic tuff or ash deposit that you see here, the silica-rich material, which is one of the necessary elements for forming things like geysers. I don't see any evidence of geysers here, but certainly do see evidence of thermal features. And based on what I see in terms of the color of volcanic material, I would say we're looking at a felsic or high intermediate silica type volcano. Welcome to the subway. This is a volcanic lava tube, and you can see the cap is still in place on the lava tube. A lava tube forms as lava travels when it's hot out of a volcano, and the top portion of it begins to solidify and keeps the material hardened underneath it. Many times the roofs collapse. Until they do, they make a really good insulated cave, and I'm fixing to walk into Subway Cave. So, this is part of the Lassen volcanic field, which is the part of the Cascadia Range, where Juan de Fuca plate has been subducting under the North American plate. Welcome to Subway Cave. As I enter into the Subway Cave, I will not be able to photograph, considering it's pitch black in there. But I wanted you to see what the actual cave looks like. Keep in mind this was a lava tube where lava traveled back when this thing erupted. So here we are at the end of the cave. It was about a 1/3 mile hike. And you can see that we have another opening for the lava tube, where this rubble here represents the collapsed lava tube roof. But you have to imagine that there was lava running through this thing back when it was active. So say goodbye to Subway Cave. Another volcanic feature you'll see is something called a spatter cone. And a spatter cone are these circular openings, usually that happen in a lava flow or a lava tube. Maybe even like a window at the top of a lava tube where fluidy hot lava can spray out. So if you can almost imagine it spraying in all directions, it's going to spatter, not splatter. Make sure you get the spelling right, spatter. And the spatter makes these features right here. This is one in Bandera Volcano and Ice Cave in Western New Mexico, and this is a really good look at what they can be. Sometimes they're smaller, sometimes they're larger. But spatter cones just are these openings where the lava can spray out, and it accumulates around the edges, making and hardening into a spatter cone. Spatter ramparts are very similar. It's same type of thing, but instead of being circular, they're linear. They're a fissure that opened up, and the crack, it represents all the debris and the crusty stuff on the side. It forms just like the spatter cone. It just sprayed out and deposited on either side. So these are super common with fissure eruptions. Another volcanic feature that you'll see is something called a hydrovolcanic eruption. This is a shot I took from that same helicopter that I was showing you, the lava tubes. And we followed that lava tube and lava flow all the way to the ocean. And this is what we saw. It was very loud because I went on a helicopter tour without the windows on. So you're well strapped in. It's really as safe as it would be without it. But the cool thing is you didn't get shots that didn't turn out right because you had to take it through the windows of a helicopter. It allowed me to see, feel, and hear how explosive it was when that lava that was so hot contacted with the ocean, the Pacific Ocean. And when it did, it super cooled that stuff and made right along here, you can start to see images even along over here. It's not just black lava, you're seeing black sand beaches. And this, I might add, is also a neighborhood that was being completely inundated with lava. So basically the real estate was useless after that point. So let's shift gears from the more fluidy types of things you'll see, meaning low silica, hot lavas, low viscosity, and we're going to shift into the lower temperature, higher silica, higher viscosity features, lava domes. If you see this, that is a clue, because this thing right here, not only is it volcanically active, it's where that thick, viscous material that's not nearly as hot as what we've just seen in the other features, and it's building up pressure. So it's what's building up in the pipe of the volcano, and eventually, if it's given the right circumstances, this thing will blow. And when it does, it'll be a massive, violent pyroclastic eruption. Another feature that happens, and it can happen with any kind of volcano, but certainly with highly explosive ones, what will happen is a volcano will erupt, and in the magma chamber, it withdraws most of its material very quickly. So the reason that's more indicative of a highly explosive eruption like a felsic or high silica intermediate is just a ton of stuff comes out real fast. So in a circumstance, you can see these in mafic volcanoes that have basalt where the magma chamber is emptied out and the thing collapses. Calderas are typically fairly large features geographically, and sometimes they can reach many kilometers in diameter. So I wanted you to see one without water, and we'll learn about one with water. There's a beautiful caldera in Oregon called Crater Lake. And the crater is actually a caldera from the collapse of an ancient volcano, much like Mount St. Helens, Mount Mazama, and it erupted about 7,700 years ago. So it's a pretty young feature. Now you might notice there's another volcano that's grown up from the bottom of the crater floor, and the crater floor is not quite 2,000 feet deep. And this is a resurgence right here. So we have a new cone that started to form after the large eruption that created a caldera. So when we look at that more closely, I need you to think about what that means. A resurgent caldera is very dangerous because it means it's still active and new volcanoes are forming inside the caldera. So if we drain the water out, you would see there's probably other cones that could be created at the bottom in different places of this system. I'm not saying that's the case in Crater Lake, but certainly is the case in many calderas. Welcome to Crater Lake National Park. Crater Lake is located in Oregon, and the big question is, why does it look the way it does? Crater Lake is the result of ancient volcanic eruptions that actually had such power that they blew out a lot of magma, lava, very, very quickly, creating a caldera, which is a very special geologic feature where the volcano collapses inside of itself. The eruption that caused this occurred approximately 7,700 years ago, but has evidence now of recent volcanism in the form of the volcano that was just indicated to you. That volcano is Wizard Island and represents resurgent caldera activity. Whenever you see that, that should send a flag up. Notice the light-colored igneous rock that's very, very characteristic of any subduction zone around the world, because you got blending of basaltic and felsic crust at a subduction zone. When you look at Wizard Island, it shows evidence of very recent eruptions, even the lava that's capping the flows at the top there. That should be very indicative of a dangerous situation anytime you see resurgent activity growing inside the floor of a caldera. All calderas basically have the same shape. They're circular. When you get this zoomed out view, panoramic view of Crater Lake, you'll begin to see there's a big gigantic rim. You need to imagine that that magma chamber collapsed inside of itself. And that's why these basically have the same shape around the world. Not all calderas are filled with water like Crater Lake, but all calderas represent ancient volcanic eruptions. So the next time you see one, you'll know how it formed. This is truly a volcanic legacy. See you at the next stop. Another feature that's important to talk about are volcanic pipes. So volcanic necks and volcanic pipes, those terms you learned about in igneous. So the pipes are the actual conduit systems that connect the magma chamber to the surface. And when they harden, they're technically called volcanic necks. But in the world of mining, they're called volcanic pipes. And what do I mean by mining? People look for inclusions that are in igneous rocks called diatreme breccia. And the diatreme breccia are rocks that break off from way deep inside the earth and that get pushed up, usually not in a lava eruption, something that's called a phreatic eruption, which is mainly water and gas. And when that happens, it brings them up through the pipe opening here and usually deposits them on land. That, or people will mine subsurface adjacent to one of these things, trying to find this right here. This is an example of a xenolith, and those are inclusions, and in this case it's a diamond. But there are many types of inclusions in igneous rocks, but for volcanic pipes, that's the number one thing that people are trying to find, are the inclusions of diamonds that formed hundreds of millions of years ago, if not billions of years ago, way deep in the mantle. So let's apply what you've learned thus far. What type of eruption would have produced this? A highly pyroclastic, felsic, or a very hot mafic? And color matters, and also you can see the ocean, you can see where some of this stuff is draining into the ocean. So if you guessed mafic, low silica, low viscosity, very hot, traveled a long way, then you're correct. All right, some hazards that you should care about with volcanoes or pyroclastic flows. These are the most dangerous of all of the hazards that we have with volcanoes. And this is an example of a pyroclastic flow right here. And notice it's coming down the side of the mountain. That's extremely scary because these things are traveling at hundreds of kilometers per hour and they are supercharged, super powerful, basically run down, plow down, and burn everything in its path. So you don't really stand a chance if you were hanging out on the side of the mountain when one of these things go. I guess the only way you would survive is if you could get underground, and then there may be hundreds of feet of material stuck on top of you that gets deposited in the form of pyroclastic ash and debris. So just know that pyroclastic flows, you're not going to see these with mafic and ultramafic. What you will see them with are high silica intermediates, which are subduction volcanoes like this one, or you will see them in felsic eruptions. So even if a volcano does not have a highly violent pyroclastic flow, it still can eject pyroclastic deposits, which are known as Tepra deposits. And these are any size of rock or fragments that come out of a volcano and are forcibly ejected through the air, travel, and then land somewhere on the ground. That's ash, lapilli, volcanic blocks, and even bombs. So let's take a look at each. This is the ash right here. This would kind of be like maybe a little bit of lapilli or even a block, but this is typically what lapilli is. And then you get a big giant bomb right here. So the size matters. Ash is less than 2 millimeters. The finer the ash, the longer it lingers in the atmosphere. Lapilli typically deposits almost like it rains deposits, and they're 2 millimeters up to 64 millimeters in range. Most of them are smaller, 2 to 6 millimeters in range, but you can get them all the way up to 64. But if you get greater than that, you got yourself a bomb. So notice I made the pictures from small, medium to large, and that is certainly the case with Tepra deposits. Look at this Tepra deposit. This is from Mount Pinatubo eruption in 1991. And notice the sky is gray. That's from ash, and that's during the day, like noontime hour. So it almost looks like it snowed, right? So you can see how this kind of ash could block out sunlight and cause some climate change. So this is one thing we care about because you don't want to be breathing in these materials. That's be devastating to your health. Another hazard are lahars. These are really secondary volcanic hazards because you have to have the eruption first before the lahar will typically form. Lahar is an Indonesian term that means rock and water fragments that are flowing down the side of a volcano. And they're caused because these things up here melt. So when Mount St. Helens erupted, very clearly created some devastating lahars, which you're seeing right here. And lahars can be flowing at tens of kilometers per hour. So they can move very fast, and then as they start to harden and reach towards the base of a volcano where the dip is lower, they can spread out and form a debris flow. They become very viscous, almost like concrete. So let's apply what you've learned. What is the very fine-grained stuff called? And if you guessed ash, you're right. The next size up would be what you would see here. And then, of course, if you get something that's huge, it would be like a volcanic block or bomb. So the location of volcanoes matters. Volcanoes can't form without a hot spot. So wherever you see the red items, these are very active volcanoes around the world. And we can certainly get new ones or dormant ones that reactivate, but these are the active volcanoes of the world. So they kind of match where we see the boundary markers of plates, whether they're along subduction zones like these all around here, rift zones, divergent plate boundaries. I might add, here's some divergent volcanoes here. Here's some intraplate volcanoes from hotspots like Hawaii, and this is going to be your Iceland area up here. These are all subduction zone volcanoes here. So volcanoes are worldwide, and we monitor them because we need to make sure that we are preparing for evacuation of humans if we were to have a catastrophic eruption. All right, so let's talk about shield volcanoes first. This is Mauna Loa, and it's by far the largest volcano, if you want to be blunt, mountain in the world. It extends 56,000 feet all the way from its summit to the bottom of the ocean floor, which makes these things the largest of any mountains of the world, certainly volcanoes. So what do I mean by total relief? If I'm holding bottled water, and this is the ocean surface, there's still the rest of the bottle underneath it. So this would be from here to here, the summit. So everything beneath it, all the way to the bottom of the ocean floor, to its summit here, that represents total relief. These are very indicative of low silica eruptions, so they're going to be usually mafic. I had to drive over this to get from one side of Hawaii to the other, and it got really cold at the top, and yes, I encountered snow. And so it was kind of an unusual thing, because then you get back down to the other side of the island, it's hot again, and or pleasant in Hawaii, actually. The simplest of all volcanoes are cinder cone volcanoes. Now you can find cinder cones on shield volcanoes that form. I've seen that on Mauna Kea, Mauna Loa, even Kilauea. That's what those vents are. But cinder cone volcanoes make this standard typical body plan where you get this shape right here. This is actually on Mauna Kea on the way up to it in Hawaii. And they have a single discharge vent. Single, that means it's only coming out one way. And so that's what makes them simplistic. So don't underestimate the explosivity of a cinder cone volcano, because they can be absolutely devastating. And that is important to know, because this is all pyroclastic material. It's just not very highly explosive pyroclastic material. You do get some pyroclastic stuff and material coming out of mafic eruptions. This is another cinder cone volcano on Mauna Kea. Classic look, right? And you probably would, if I asked you to draw one at the beginning of the lecture, this is probably what you would have drawn. This is one in New Mexico, Mount Capulan, and you can see that it has that same body profile, and it has its crater up here. This is the road you can take from the park headquarters all the way to the top to view the crater of the cinder cone volcano. Another cinder cone volcano I want you to learn about is Bandera Volcano. It erupted about 10,000 years ago in western New Mexico, in Grants to be specific. And this is not too far, and actually near the section of the far western part of the Rio Grande Rift zone where the North American plate was separating. This is the spatter cone that you learned about there. You can remember how they formed a lava tube opening and it sprays out. This is the lava tube that's collapsed as you take the hike to the ice cave, and so all this debris down here used to be the ceiling or the roof of the lava tube. At the base of the lava tube, you take multiple flights of stairs down and you end up in the Bandera ice cave, which is really cool to see. This is a great tourist stop if you want to see it. It's not expensive to see. It's privately owned, I might add. But the green color comes from the biological material that gets embedded in the ice. But this is a really interesting place. The point is that the lava insulates even water instead of lava now. It stays below freezing here all year round, so it retains ice. And many ice caves do this around the world if they're basaltic. Let's get to the third body plan. So we looked at the shield body plan, which is a very wide feature, biggest volcanoes in the world in terms of their width and overall total relief. They're also not going to produce the real violent eruptions. And you get a little bit more violent, which is cinder cones, single vent. Well, now let's move into composite volcanoes, which have multiple vents. Composite volcanoes form over many eruptions, layer after layer, and they have multiple discharge vents or conduits that bring magmatic material to the surface. So they're very complex. They form along major subduction zones. Here's Mount Shasta in northern California, and you can see the top of a crater here. I might add there are glaciers here. So if we were to have an eruption, you could imagine, oh yeah, that could probably form a lahar. All right, Mount St. Helens is one of the best stories that we can talk about with composite volcanoes because we have so much data on it. It erupted on May 18th in 1980. There were scientists that were studying this mountain for a year before this thing erupted. And there was a man that was on this face right in here that was from USGS. He was stationed on the mountain measuring the tilt of the mountain, seismograph issues, meaning is it producing earthquakes. And unfortunately, the morning of May 18th, this thing let go, but it didn't let go the way that scientists predicted, which should have been straight up. But the lateral pyroclastic eruption basically lost this side of it, and we'll show you how it worked. Taking a look at this, notice that the shape of Mount St. Helens, this is before the 1980 eruption, right before it, this is what it looks like today. So you lost that entire front north flank face. And I might add, here's a new lava dome forming. That's a clue and dangerous. And you definitely want to consider what this looks like. I might add that all of this material, there's a combination of lahar and pyroclastic ash that's now deposited in this whole section. This used to be an old growth forest, and now it's not. Now they're regrowing a forest in the region, and I'll show you that in just a second. The pyroclastic flow that came out of Mount St. Helens decimated an old growth forest, and this is what you would see if you went out there. These huge trees, the old growth type trees, snapped off literally at their base. And these are shots I took while I was at the Johnston Ridge Observatory, and was just so incredibly and profoundly touched by how severe this eruption was and how fast this thing was decimated. We're talking about within 10 minutes, this process was basically done. And the pyroclastic flow just took out many kilometers away from the volcano, anything it touched. This is the blast zone when you're driving into Mount St. Helens, and now they've replanted the old growth forest because this happened in 1980, so we're looking at over 40 years since this thing erupted, and it's been enough time to get repopulation of the trees back. If we have another eruption similar to 1980, unfortunately this blast zone will likely have the same outcome that the first one did. This is a shot from USGS of some of that pyroclastic material, and this stuff is super thick, meaning it is tens of feet thick. It's not just one little tiny layer. So this was all the stuff inside the volcano that was penned up behind the pipe, the cork that got uncorked when the lava dome failed. At the top of Mount St. Helens even today, and it's like a third shorter than it used to be because it lost that much of the mountain in 1980 during the eruption. Can you see the snowfields up here? this material, what melted and created this massive lahar that went not just in this area, but found the path of least resistance, which have been creek beds and river beds, specifically like the Toutle River Basin, and wreaked havoc for hours after the eruption. So secondary threats like lahars from volcanic eruptions can cause long-term problems, not just the day or days after an eruption, but years. Let's show you how tall this lahar got. It was like a raging flood of mud. This is the tree line. Here's your creek bed, and here is a person. And that gives you perspective of understanding that this thing was huge. And so everything's kind of just like buried in place. This is the famous A-frame house that's near Mount St. Helens, and the lahar buried this, and there's multiple stories in an A-frame house, and this is the very top part of it. So the rest of it's consumed, and they'll never be able to use this for a house structure. And this is your Toutle River Basin right here, and most of this deposits are lahar deposits. I am at the buried A-frame and the Maple Flats volcanic site. Construction for this A-frame home started in 1978, and on May 18th, 1980, the home was about 3 days from being fully completed. All that remained to be finished was putting in the chimney for the wood stove and some upstairs fixtures. These were to be done the week of the eruption. The owners of the A-frame and the gold house behind me had left Maple Flats on May 17, 1980, not because of volcanic action, but for other personal reasons. Many of the people who lived in the 12 homes that were directly across the road were at their residences at the time of the eruption and were given 2 hours to take what they could from their home before they had to evacuate. They could not return after this period of time because it would not be known how soon the area would be inundated by a lahar that would later take their homes and fill up the A-frame that you see right here. The A-frame was buried by the mud flow at about 5 p.m., almost 8.5 hours after the eruption of Mount St. Helens. Approximately 200 tons of silt, mud, water, and ash filled up the basement of the structure and the first floor. The flow had the consistency of wet cement and weighed 2 to 3 times that of water. The temperature of the flow was over 100 degrees as it passed from Maple Flats and headed for the Cowlitz River and later into the Columbia River. The mud flow did not head down the North Fork of the Toutle River Basin until about 1:30 p.m., 5 hours after the eruption. 2 miles down the valley, the mud flow reached speeds of over 70 miles an hour. So much of a problem in this area that local water treatment facilities use this for drinking water, the rivers, and the rivers can get contaminated every year with lahar deposits. This happens all over the world. Philippines from Mount Pinatubo still have problems all these years later. It erupted in 1991 with lahar deposits and even new lahars forming during wet season like monsoon season. This is a problematic issue, and when I found this when I was out researching Mount St. Helens in the field, I was struck by the fact that they had to build a special dam to capture some water, to add a filtration system to help remove some of the lahar deposits before it went to the treatment plant for full treatment for drinking water standards. When you go to Mount St. Helens, you need to drive all the way to the Johnston Ridge Observatory, and it's named that after David Johnston, who's the geologist that lost his life on the mountain that day. And there is a really great museum, even the original seismograph showing the 5.1 earthquake that's thought to have initiated the collapse of the lava dome and created the big landslide, which then led to the Pyroclastic Eruption and then helped melt the ice packs leading to a lahar. So Johnston Ridge Observatory is really a cool place. When you get there, you can learn about the silent zone. The silent zone are areas of land, specifically some of the mountains near Mount St. Helens, here's Mount Rainier, Mount Adams, and there's, various different mountains, and Mount Hood. There were hikers on these mountains who literally could see this eruption happen, but couldn't hear it because they were in the silent zone. So what is the silent zone? Basically, you get sound waves from these massive explosions, and it sends that sound waves up to the upper atmosphere and it bounces back down. So if you were in this section right here, the sound wave, you would have heard it here. You could not have heard it in this section right here. And this was a phenomena actually witnessed and documented and has been since seen in other places. So let's get to types of volcanic eruptions and look at how they are different. And I'll show you some video footage about how they each work. So I want to start off by saying the names simply are where they're most common in the world, or a name applied to them based on a historic frame. So this would be an actual Volcanian eruption right here, but we're going to get to all of them in just a minute. But that's pyroclastic material. We're going to start from the least pyroclastic to the most pyroclastic. So we'll start with Hawaiian. This is the vent that I've been talking about in Hawaii on Kilauea that's so active, and it's the one that produced a lava tube that I traveled in the helicopter to see this hydrovolcanic eruption. These are the least violent because the lava is extremely hot. It's very mafic, and they travel a long distance from their source, usually via lava tubes. So you can have Hawaiian eruptions elsewhere besides Hawaii, but that's where they're most common, and that's how they got their name. This is the type of lava eruption you'd expect with Hawaiian. Very hot, very fluidy. This is a video taken by USGS in Hawaii. Fissure and Icelandic eruptions can also happen anywhere in the world. I might add you can see them in Hawaii, but this is a fissure that I took a picture of in Iceland. And it would have had this type of lava coming out of this when it erupted. And typically these are associated with mafic eruptions, certainly along the flanks of shield volcanoes. You'll see this happen, and they get heated up and it becomes weak crust and the lava flows out. So as you're watching this Icelandic fissure eruption, very similar in terms of fluid, like hot material. The difference from Hawaii to fissure eruptions are that they're along a fissure opening or a crack. You can certainly see fissure eruptions in Hawaii. Looking at a long linear crack in the ground as opposed to just a vent. There you go. That's a really good shot of seeing a fissure eruption. So Strombolian eruptions are based out of a place in Sicily. It's an island. For example, Mount Etna. And it produces these types of beautiful eruptions. So a little bit more pyroclastic-y than what we would see in a fissure or a Hawaiian eruption, but they're still very mafic, and they make these lava bombs that come and eject and just make this beautiful, almost fireworks display. But they're a little bit more explosive, which means they have a little bit more silica. They're not quite as hot as you would see the others that we've learned about thus far. So each time we're graduating up a little bit more in explosivity, a little bit more silica, a little less temperature. This is a good look at a Strombolian eruption, and you can see the fireworks-like display, a little bit more explosive than Hawaiian and Icelandic / fissure eruptions, but still very mafic and extremely hot. Which brings me to phreatic eruptions. These typically are steam eruptions with water, so lots of water vapor with minimal lava ejection. You can have some. They produce intense ash and are usually precursors to a much larger Volcanian or Planean eruption. But this is what a phreatic eruption looks like right here. This is in Manila, and this is the one that happened before the big pyroclastic eruption in Mount St. Helens. A famous phreatic eruption is Krakatoa. Even the name Krakatoa sounds amazing. This erupted in 1883, and it was so intense that it caused a big caldera basically to form. So this used to be a bigger island, and you can imagine as that collapse occurred, it created a massive displacement of water, which formed a giant tsunami, and that's what killed most of the people. So this is in Indonesia, and this was caused by a very large phreatic eruption. When we think about volcanic eruptions, there are bigger than phreatic. They have lava, they have pyroclastic material, so they're not as hot. They have higher silica. They produce more pyroclastic material. This is a volcanic eruption in Krakatoa, and Krakatoa is still active, I might add. And then you can see another volcanic eruption here in Japan. You're looking at a small volcanic eruption producing a pyroclastic cloud. Which brings us to the most explosive of all volcanoes, called Planean. And Planean volcanoes in size just are immense. So they have the high silica intermediates and even felsic eruptions. They make towering columns of volcanic ash that extend many kilometers into the atmosphere, tens of kilometers into the atmosphere. They usually have a pyroclastic flow. They can produce lava that may not travel as far because it's not as thick, but it can create and wreak havoc on anything in its path. One of the most famous of these eruptions is Mount Vesuvius, which is often called Pompeii. Pompeii is not the volcano Mount Vesuvius is. It erupted in 79 AD, but it did bury the towns of parts of Herculaneum and Pompeii right here. Here's Mount Vesuvius, and I might add it is still there today. And this is an artist depiction based on Pliny the Younger sketches that were found finding this material, because Pliny the Younger actually documented this and wrote it in his journal and went to safety during the eruption. And his work is why this thing is called Planean, because it's named after him. Unfortunately, there's a whole civilization that was captured, and many movies have been made about it. But this is Pompeii Herculaneum, and you can go there to see what's been dug out archaeologically. And there's over 1,150 remains of body cast of humans and animals and artifacts of all kinds, the people that lived there. So you have to imagine that Pompeii and Herculaneum were thriving cities of their time, port cities, and so it was happening things going on there. It was the place to be. These are hard images, but the realities of Mount Vesuvius, and the lesson that you need to take away from this is that it could happen today if we have a Planean eruption near a civilization. The good news is we have warning systems in place now. Hopefully we could evacuate. I know these people had ample warning that this thing was going to erupt. They just had no idea it would erupt like this. So it buried them under feet of pyroclastic material. So now we're going to learn about the different types of eruptions. And remember, we started with our Hawaiian and Icelandic fissure, then Strombolian, Phreatic, Volcanian, and Planean, and they are getting more intense as we go through each one of these. So now that we've learned about all these volcanic eruptions, let's apply that to something called the Volcanic Explosivity Index Scale, VEI. And VEI measures the explosivity, how much ash and pyroclastic material comes out, the height of the ash plume, but what's not really a huge factor is how much lava comes out. And it is a logarithmic scale, so it goes from 0 all the way to 8, and each time you're getting 10 times more material that comes out. So what do I want you to know about VEI? The name of the eruption, its rating, and its frequency. So a non-explosive is a rating of 0. That's like this eruption in Kilauea today, and it would have a 0 on the VEI scale. It happens daily across the world. Things that you would expect to, or volcanoes you would expect to produce that, are Hawaiian and Fissure Icelandic eruptions. A 1 is a gentle eruption. This would be like a Strombolian eruption, and they happen daily across the globe. There are minimal pyroclastic debris ejected, but since this does put out lava bombs, a little bit more explosive than your non-explosive zeros, you do get some of that there. Explosive eruptions, these are 2s. They eject volcanic material up to 5 kilometers in the atmosphere. I really don't care if you know that number, 5 kilometers, but the point is it's more explosive. These happen weekly on average somewhere around the world, and they would represent weak Volcanian eruptions. So we talk about severe eruptions. These are a 3 on the VEI scale. They happen annually across the globe, and we're already seeing a pyroclastic cloud that looks like this. So this is a Volcanian eruption for sure. And you can start to get material as high as 15 kilometers in the atmosphere from these types of eruptions. So a cataclysmic eruption is a 4 on the VEI scale, and they happen once a decade, every 10 years, and they start to eject pyroclastic material up to 25 kilometers into the atmosphere. This would be a strong Volcanian, maybe a weak Planaean. When you reach a 5, you've got your standard Planaean eruption, typical one. A 5 is proximal eruption, and these have ash plumes that can reach 25 kilometers and higher. This is what Mount St. Helens was in 1980. So they happen once a century, every 100 years. A VEI of 6 is a colossal. So a 6, 7, and 8, there are colossal words in each one of them. And remember, each time we're going up, there's 10 times more material inside of them. They eject, just like our 5s, much greater than 25 kilometers into the atmosphere of pyroclastic material. They happen once a century, and they're very strong Planaean eruptions. So an example would be for Pinatubo. So when you think about Mount Pinatubo in 1991, it's a subduction zone volcano, and it erupted over 300 feet of material that got deposited on the ground of pyroclastic tephra. The removal of this huge amount of stuff so fast created a caldera. The ash in the atmosphere lingered and actually helped drop global temperature by about 0.5 degrees for around a year or so. So this is an actual picture of the Pinatubo eruption in 1991. So let's take a look at one of the problems of the Mount Pinatubo eruption. It also coincided with a typhoon. Bad luck, right? So now you got wet ash, and it mixed with all the material that was there in the wetness, and it created just intense lahars. Still problematic today from this eruption, lahar deposits being repicked up during their typhoon season. And I might add, do you see what looks like a lava dome here? That's a clue, because this is definitely a subduction zone volcano. You would expect that to happen, and that's where the source of the pyroclastic material came from. This is the Air Force Base in Pinatubo called Clark Air Force Base, and then there's a naval base there as well. And this is what happened to them. Look at the ceilings of the hangars and the buildings collapsed from the wet ash that got there. Lahars buried these areas. The good news is we learned a lot from the 1980 Mount St. Helens eruption, which helped with warnings. So I believe we keep getting better as scientists about this, and I think that that's the future of trying to help get people evacuated before these terrible events happen. Here's another shot of some of the lahar devastation and ash deposits, pyroclastic tephra from Mount Pinatubo. This is another shot of looking how devastated some of these areas were by lahars. Lahars follow the path of least resistance, typically, like a creek bed, riverbed, road, things of that nature. You can certainly see this in this USGS photo of the Mount Pinatubo eruption. All right, let's get to a 7. We went from colossal at a 6, now we're at a super colossal, which is a 7. Once a millennium, every 1,000 years, we get an ultraplanean eruption. And these things are devastating. So We don't want one of these because they're so dangerous. And thinking about that, it would be terrible to have one in modern day, especially around civilizations, which moves us into the most devastating of all VEI rated eruptions, which is megacolossal, and that's a VEI rating of 8. This produces pyroclastic material in an unprecedented way, and it happens once every 10,000 years. They are ultraplanean eruptions. I mean, these are the biggest, and they're open-ended. So remember, each time they get 10 times greater in size, well, 8s are open-ended. So Mount St. Helens was a 5, Pinatubo was a 6, the Yellowstone Caldera was an 8, and there's even one from the Yellowstone Caldera that was even bigger. And we'll learn about them now. There's a supervolcano in Yellowstone that's a volcanic field that represents multiple big eruptions that happen. In VEI language, we've had 2 8s and 1 7, so 2 megacolossals and 1 supercolossal. The largest of the 3 is the one that put ash deposits all the way down through Texas, way down here. So here's Yellowstone, and here's us down here, or the ash deposits down in the southern section near Texas and Mexico. That was the Huckleberry Ridge caldera, and that was a megacolossal eruption that dated 2.1 million years ago. There was one that was a smaller eruption in the same area that was called the Island Park caldera, and that erupted 1.3 million years ago. That was the supercolossal, or a 7. The one that created the caldera in which the geysers exist today is the one that formed the Yellowstone caldera. So if you visited the park, that's what you would be in. That was 640,000 years ago, and it was the second largest eruption of Yellowstone. Let's take a look at Huckleberry Ridge, and this created many of the large, beautiful landscapes that are out there where the Snake River Basin flows through parts of Yellowstone. And they helped create this very felsic plumbing needed for the Yellowstone geyser field. But remember, the geyser field's actually formed in the Yellowstone caldera. So that means we need to take a look at each of the boundary markers. So the boundary marker of the Yellowstone caldera is this purple one that I'm putting my mouse on here. This is the Island Park. This blue one marks the boundary of the park. And so what I want to put into here is to point out that the pink is all the rhyolitic material, the yellow is basaltic material. So you do have some basalt in the park, and if you get into the northern section way up here, Mammoth Hot Springs, notice there's no pink up there, so there's no way that you can have the material or plumbing necessary to make geysers. That's why there's so many geysers here. We still have an active hot spot that's there. This is where all the rhyolitic material got deposited. Again, Yellowstone megacolossal eruptions produced ash that extended a long way from the park as far down as Texas. And you can understand, here's like the Mount St. Helens, how far it deposited stuff. Point being is if we had one of these today, you can imagine the implications to human health and the environment. When you get to Yellowstone, you can see evidence of the megacolossal eruptions. This is a big tuff cliff that it's a stop you can look at. So it's volcanic tuff, which is a form of rhyolite, and it's very, very thick, indicating the pyroclastic Tepra deposits that were laid down during the Yellowstone Caldera eruption 640,000 years ago. Same thing with this outcrop of rhyolite in Yellowstone, and this is all felsic material. So while you don't see a volcano when you go there today, you see all the evidence because the volcano literally blew away and all of its material got deposited elsewhere. Highly explosive, the most explosive types of eruptions, megacolossal. There's still another example of a pyroclastic eruption, and that's Lake Toba in Indonesia that erupted 77,000 years ago. And I want to point out, this is it right here. That is a caldera, just like Crater Lake that you learned. So Indonesia has a lot of issues, and you'll be learning when we get to earthquakes about tsunamis and an earthquake that happened not too far from there in Sumatra. These are devastating events. This was a mega colossal eruption, the largest one besides the Yellowstones, that happened at 2.1 million and 640,000 years ago. So what are the volcanic issues, the takeaways from this? Pollution. You get fog, ash, hazardous gases, Lahar deposits. They all pose threats to human health and the environment. And this is a shot in Hawaii. You would need a gas mask here. And these lava flows could certainly impact human structures, but just the gas itself can put pollution not just in this location, it can blow across the island. So I've been to Kona, which is on the other side of the island from this park, the Hawaii Volcanoes Park, and there are times where bog can reach the other side of the island. Other hazards. Lava flows can bury homes and entire subdivisions. This is an example of, in 2019, a famous place that I love to go when I would visit Hawaii just got buried by lava. It expands the size of the island. That's good in a way, but it takes out this real estate. So this can be a problem, but the good news is people had warning and they had time to get to safety unless they chose not to. Mass wasting is always a problem with volcanoes. You can, as we learned with Mount St. Helens, you can get earthquakes that can trigger landslides, that can also unleash lava domes that are plugged up. You can get lahars and debris flows, even avalanches for that matter. So all of these things are associated with the hazards of volcanoes. There's some benefits to volcanoes though. This is the plantation fields for the Kona Coffee Company on the island of Hawaii, and as your volcanic material starts to weather, the basalt, it becomes very, very fertile, and it makes great fertile land for agricultural use, in this case for coffee. If you've never had Kona coffee, yummy. It's so good. Unfortunately, volcanoes can lead to climate change, and there's a couple of times in geologic past where volcanism is associated with climate warming, climate cooling, both. Dinosaurs didn't just go extinct because of meteorites. There's also clear evidence that there were changes with volcanic gases, probably before the meteorite at Chicxulub happened. So that's important to think about how massive volcanism could affect global climate conditions. We want to conserve these volcanic places not only because they're beautiful, but they tell an ancient story. Some of these places are called World Heritage Sites, which are protected internationally. And this is Crater Lake. You've already seen this once, but many volcanic landmarks around the globe are protected because of their importance to the history of geology. We monitor them because we care about these active volcanoes around the world and their volcanic monitoring stations and active volcanic areas. And the United States Geological Survey sends people all over the world to monitor active volcanoes and go on site to try to help with prediction of when is a warning needed for an area for evacuations. So let's apply what you know. This is in Yellowstone National Park, so it's in the Yellowstone Caldera. This is Artist Point, and I might also highlight that this is all very light-colored ash and rhyolitic material. While this is a beautiful waterfall, it's cutting through this high silica material, and the thickness of the material is the testament that I'm wanting you to see. It's there because of the mega colossal eruptions. Subsequently, all of this rhyolitic material links back to what you learned about with hydrothermal features like geysers and mud pots, fumaroles, and hot springs. But geysers could never form if they didn't have the right plumbing, which is that high silica material that forms geyserite or sinter. And that is what is caused by this material here. So I realize you might have questions or concerns, and you can feel free to reach out to me. This is a volcanic crater in New Zealand near Rotorua. And I'm going to leave you with a nature moment and then come back with a few more comments after that. I sure do appreciate your time and your commitment to learning about volcanoes and volcanic hazards. I'll see you in earthquakes. Bye.